Journey into the heart of the sun. Imagine gazing up at a blazing star that has shaped life on Earth for billions of years, a fiery giant that lights our days, warms our planet, and holds secrets we're only beginning to unravel. This is our sun, a dazzling ball of plasma at the heart of our solar system, radiating energy that has inspired myths and driven scientific discovery. Today, we're embarking on a thrilling voyage through its scorching layers, using cutting-edge technology to peer deeper into the sun than ever before. From its shimmering corona to its churning surface, join us as we uncover the mesmerizing phenomena that make our star a cosmic marvel. A cosmic time machine, the sun's ancient light. When you look at the sun, you're not seeing it as it is now, but as it was 8 minutes and 20 seconds ago. That's how long it takes light to travel 150 million kilometers from the sun to Earth. But the story of that light is even older. Photons born in the sun's core take 10,000 to 170,000 years to fight their way through its dense layers before bursting into space. It's like receiving a postcard from the distant past, carrying clues about the sun's inner workings. To explore this star, we'll use images from NASA's Solar Dynamics Observatory, launched in 2010, to study the sun's dynamic surface and atmosphere. By capturing light across different wavelengths beyond what our eyes can see, the SDO reveals hidden details that transform our understanding of this celestial powerhouse. The corona, a fiery crown. Let's begin with the sun's outermost layer, the corona, a glowing halo of plasma stretching millions of kilometers into space. Using extreme ultraviolet light at 19.3 nanometer wavelength, the SDO reveals the corona's intricate beauty, glowing at a searing 1 million Kelvin. During a total solar eclipse, when the moon blocks the sun's bright disk, the photosphere, the corona becomes visible to the naked eye, a radiant crown encircling the darkened star. But the SDO's images show far more detail, capturing the corona's dynamic dance of plasma. Within this fiery crown, dramatic events unfold. Solar flares, colossal explosions of electromagnetic radiation, erupt when tangled magnetic fields snap and reorganize. These flares, visible at 20 million Kelvin, release energy that could dwarf entire planetary systems. In August 2022, the SDO captured a week of intense flare activity, a hypnotic display of the sun's raw power. These bursts are both beautiful and terrifying, capable of disrupting satellites and power grids if directed at Earth. Darker patches in the corona, known as coronal holes, reveal another marvel. These regions of cooler, less dense plasma have open magnetic field lines that stretch far into the solar system. Unlike the closed loops that trap plasma near the sun, these open fields allow solar wind, streams of charged particles, to escape. When these winds collide with Earth's magnetosphere, they ignite dazzling auroras, painting the polar skies with shimmering greens and purples. Using extreme ultraviolet light, the SDO highlights these holes, showing us how the sun's breath shapes our cosmic neighborhood. Next, we encounter solar filaments, or prominences, massive loops of plasma that arc hundreds of thousands of kilometers above the sun's surface. These glowing structures, large enough to make Earth look like a speck, can form in a day or persist for months, held in place by the sun's magnetic fields. Watching a filament twist upward in SDO footage, sped up to show minutes a second, you can feel the sun's restless energy. Some of this plasma doesn't escape. Instead, it cools in the corona and falls back as coronal rain, glowing droplets that cascade toward the surface at millions of degrees. Unlike Earth's gentle showers, this rain is a spectacle of molten fire, a reminder of the sun's alien nature. Coronal mass ejections, cosmic catapults. Then there are coronal mass ejections, where tightly wound magnetic fields snap like elastic bands, hurling billions of tons of plasma into space. SDO footage at 30-nanometer wavelengths captures these events forming and erupting, a breathtaking display of cosmic power. A powerful CME aimed at Earth could cripple our technology, making these phenomena both awe-inspiring and a call for preparedness. Their frequency ebbs and flows with the sun's 11-year solar cycle, a rhythm that governs its activity. Moving inward, we reach the transition region, a thin layer just 100 kilometers thick between the corona and the chromosphere. Here, temperatures soar from 8,000 Kelvin to 500,000 Kelvin, hundreds of times hotter than volcanic lava. Imaged at 160 nanometer wavelengths, this region is a fiery boundary where the sun's atmosphere shifts dramatically, preparing us for the layers below. The chromosphere, dancing spicules. Deeper still lies the chromosphere, a 1,700-kilometer thick layer glowing in 170 nanometer ultraviolet light. Here, we find spicules, jets of plasma shooting upward at 100 kilometers per second, faster than sound, and stretching taller than Mount Everest. These swaying, grass-like structures form and vanish in just 5 to 10 minutes. For years, their origins puzzled scientists, as magnetic fields should trap such charged particles. In 2017, researchers discovered that neutral particles provide the buoyancy needed for spicules to break free, a breakthrough that reshaped our understanding of the sun's dynamics. The photosphere, the sun's surface. Finally, we arrive at the photosphere, the sun's visible surface, best seen in 400 nanometer visible light. At 400 kilometers thick, it's not a solid boundary, but a roiling sea of plasma, the fourth state of matter, making up 99.9% of the universe's matter. The photosphere appears sharp from Earth due to its distance, but up close, it's a turbulent expanse of ionized atoms and free electrons. Dark patches called sunspots dot the photosphere, cooler areas where powerful magnetic fields trap heat. These spots, seen in images from the Swedish Solar Telescope, often align with solar flares, linking surface and atmospheric activity. Nearby, solar granules, 1,000-kilometer-wide cells of churning plasma, rise and fall in a cosmic convection dance, moving at supersonic speeds of 7 kilometers per second. These granules, visible as grainy textures in SDO images, are the tops of convection currents, similar to those driving Earth's plate tectonics. Sadly, our journey stops here. Beyond the photosphere, the sun's interior remains a mystery, too dense for current imaging techniques. Yet, by using visible and non-visible light, we've uncovered a star alive with activity, exploding flares, vast coronal holes, swaying spicules, and shifting granules. Each wavelength reveals a new layer of this cosmic giant, showing us what our ancestors could only dream of. The sun is more than a light in the sky. It's a dynamic engine of plasma and magnetic forces, shaping our world and challenging our understanding. As we stand on the cusp of new discoveries, who knows what deeper secrets we'll uncover next? Perhaps one day we'll peer into the sun's core, revealing the heart of the star that sustains us. For now, let's marvel at what we've seen and keep exploring the cosmos. subscribe to Beyond Earth, hit the bell icon, and join us for more stellar adventures. Thank you for watching, and let's keep chasing the wonders of the universe together.